Hey guys, today we're going to think about what it means to apply math and physics in different dimensions for games. There's a lot that goes into creating and optimizing 3D worlds. Some of it can seem really intimidating and overwhelming, but I think if you can reduce those concepts to 1D and 2D physics, you'll see how we can build on those principles for 3D and even 4D worlds. Working in higher dimensions just means we're adding more variables and accounting for them. So while we may need to do quite a bit more accounting when we move from 2D to 3D or 3D to 4D, there are core principles that don't change. So let's work from the ground up together and start with the simplest system possible, a one-dimensional game. All one dimension means is that we have one position variable on one axis. Let's call this x. Our character can move along the x-axis to the left or right, but it can't move up or down or jump. It's stuck on this line. In this case, a positive velocity means we move to the right, while negative means we move to the left. We might also define a maximum speed it moves at, along with an acceleration to define the rate it speeds up and slows down. With these values, we can find its position by adding its current position to its current velocity times time plus 1/2 its acceleration multiplied by time squared. So for each time step or frame, we keep plugging in the character's position, velocity, and acceleration to this equation to get the position we should render the character at for that frame. Most engines will handle the frame rate and even all of the movement calculations for you, but if you're doing something like working from scratch in OpenGL, you'll have to make sure you have a stable frame rate for this to work. But let's add some things to this 1D system. Let's say there's another dot on the line that's moving towards me. I run into it and we both get knocked back. To detect the collision, I only need to check if my position is equal to the enemy's position, and that's it. But how far do we get knocked back? Well, we can use the conservation of momentum to know how we should move. And momentum requires that we know the velocities of each object, which we do, and their masses. So we can add a mass attribute to each dot. So if I'm 100 units of mass and he's 1 unit of mass, and we're both moving at the same rate, I'm going to send him flying. What's important to note, though, is that mass is completely independent of the world's dimension, just like hit points, scores, inventory, and many other attributes. Think about minimizing duplicated logic. In other words, if we want to port this 1D game system to 2D, we need to think about what needs to change and what can be left alone. In this case, our masses can be left alone. So we don't need to worry about those kinds of variables for the rest of this video. But let's go ahead and make this into a 2D game. Let's say we have a 2D game with a block that can move right and left and bump into things. But now we have a variable called y, meaning we can jump and move up and down. What changes in terms of our calculations? Well, the left and right movement is still exactly the same. We don't need to touch the y variable for that. But when we jump over things, we follow an arc that goes up to the side and down. This is where we separate our velocity into horizontal and vertical components. We use the same equation for position as before, but we solve for the x position and the y position separately to find the final position. So to find the y position, we plug in the acceleration due to gravity for a, which is negative 9.8 meters per second squared in real life, but it could be anything that makes sense for your game and your game's feel and controls. Anyway, we get the angle of our jump relative to the ground, call this theta, and plug in our character's velocity times sine theta for our vy component, and then our character's initial y position. To find the x position, there is no horizontal acceleration while they're in the air. Gravity only pulls you down, not left or right. So we just take the velocity times cosine theta to get our Vx component, times the time, plus the character's initial x position. Solving for the x position is actually exactly the same as our 1D equation, since our theta would always be 0 degrees, and the cosine of 0 is 1, so our velocity would be completely unchanged. In reality, games implement jumping and movement in many different ways, but this is what's happening in theory. All right, now let's add Z, so we're in a 3D world. Our movement and physics calculations seem like they would be more complicated, but they're still the same, just with more variables. This time we calculate an x and z component for the horizontal velocity and calculate the y component exactly the same as before. These axes are just names though. You may have the z-axis oriented vertically with x and y being horizontal. But let's say this angle theta represents the direction we're facing, and this angle alpha represents the angle that we jump off the ground. So our x velocity is v times cosine theta times cosine alpha, and our y velocity is v times sine theta times cosine alpha, and our z velocity is v times sine alpha. I'll give you a moment to look at this picture and absorb that. It took me a moment. We can use these different velocities to find our x, y, and z positions, which we combine to get our overall position, just like in the 2D system. These basic calculations aren't so bad, but in a 3D world, you have to deal with the dun-dun-dun camera. The camera is pretty straightforward and linear in most 2D games, but the 3D camera requires us to rotate the entire world to match what the player expects in their view. There's no point in space called the camera. That's just an illusion to help us visualize what it's doing. But let's learn how to actually do this. Let's learn the math behind it. So we can manipulate 3D views with matrices. They can translate objects to different positions, stretch or shrink them, and rotate them. So let's look at an example to see what I'm talking about. So first is our translation matrix. This can move objects around the screen. It's a matrix with a diagonal of ones, and the change we want for each variable is in the last column. When we multiply this by our position vector, we move the character's position. If we want to scale the character's model to make it bigger or smaller, we change these ones in the diagonal. It's interesting to note that we can also do this in 2D with a 3x3 matrix and in the first dimension with a 2x2 matrix. The math is exactly the same for both translation and scaling. The other thing to note is that our characters usually will not have just one point, but will be a collection of points in 3D, so we'd apply this matrix to all of those points. And there's also other optimizations to make these calculations faster, but that's the basic idea of what's happening. But let's look at rotations, which are a little bit more complicated. Let's pretend our camera is pointed at the position 1, 0, 0. So if we rotate 90 degrees relative to the z-axis, so pretending that the z-axis is like a skewer, and we rotate 90 degrees, we should end up looking at 0, 1, 0. So this is the rotation matrix for a z-axis rotation. Just accept it for now. Let's plug in 90 degrees to the angle and multiply it by our initial position vector, which gives us a resulting vector of 0, 1, 0, which is what we predicted. So we could take any three angles about the x, y, and z axes and multiply all of those matrices together with our vector to do more complex rotations. The important thing to remember, though, is that the order of multiplication does matter for matrices. But now let's say we want to start at 0, 1, 0. We're facing at 0, 1, 0, and we rotate 90 degrees relative to the y-axis. In this case, we're adjusting our orientation and the way we're facing, but we're not going to move our arrow. If this were a 3D object, our position would stay exactly the same, but our normal vectors would change. The normal vector is the vector that is perpendicular to a face of a 3D object, and all 3D objects with many polygons will have many normal vectors for each face. To simplify this, let's say our object is a simple 2D disk in 3D space. We'll have our position at the disk center and then a unit normal vector sticking out of one of its faces. So this is the vector we're multiplying by in all of these matrix calculations. The center of the disk will move only if we apply a translation matrix, and the radii will stretch and shrink if we apply scaling. So if we rotate this disk 90 degrees relative to the y-axis, it's going to face from the side to facing down. Be mindful of edge cases though when you use rotation matrices, since you can experience gimbal lock and get some weird flipped results, which is something I discussed briefly in my quaternions video and is one reason why many developers will use quaternions, but I think for our purposes these are easier to visualize. And there are many more techniques for 3D systems. Things like collision detection get more interesting and complex, but when you're watching other tutorials or reading textbooks on those topics you're interested in, remember to try and reduce it to simpler cases like a 2D world and just see what has to change for the 3D version. I think it makes tougher concepts much easier to visualize. For example, with these rotation matrices, try them in the 1D world and try them in the 2D world to get a better handle on why they work in 3D. Anyway, to see how well we can apply this knowledge now, let's briefly think about the fourth dimension. I'm going to link some of my favorite videos on 4D geometry since it's a way bigger topic than we can accurately cover today, but let's at least try to understand what the fourth dimension means. So this is a hypercube, the fourth dimensional counterpart to the cube and the square. Some people think the fourth variable is time, since we can only appreciate the full geometry if it's in motion, which requires the element of time. It's important to realize this image is a 2D projection of the 3D projection of this 4D object. When we render graphics on a screen in games, we're projecting 3D objects to a flat 2D state, almost like casting shadows on a projector. As 3D viewing human brains, we can only grasp these 4D shapes in 3D slices, which we view on the screen in 2D. Anyway, there's another way to view the fourth dimension other than time, which is illustrated really well in an upcoming game called Mie Gakure. In this case, the world you're seeing is one 3D slice of a four-dimensional world. If we have X, Y, Z, and W to define our position instead of just X, Y or just X, Y, Z, we need to phase out one of those axes so we can see a projection of a viewable 3D space. So we might be looking at the YZW or XYZ or XZW slices. And the math and physics we discussed would still be valid in this 3D projection. The key difference is that rotating your view of this 4D world can be kind of brain-bending. There's some other crazy stuff the creator discusses in his videos, like how he uses tetrahedral meshes instead of triangles, so definitely check out his games channel for more in-depth, better explanations. Anyway, guys, hopefully some of this helps you think about game physics in a different way, and maybe as you work through your studies or other tutorials, you can visualize these higher dimensional concepts more clearly. If you want to learn more in depth about 3D and higher dimensional math, definitely go through course material for multivariable calculus and linear algebra, because at this level, you really need those solid fundamentals for 3D game programming. And I'll definitely go more in depth on topics that you guys request, so definitely let me know what you'd like to see more of in the comments below. And if you want to actually learn how to make and apply this stuff, we're gonna have another challenge on the subreddit where we make a multi-dimensional game. Everyone is welcome to try. You can do as much or little as you like. You can team up with people, and when the challenge is over, I'll feature submissions on my coding stream and then live stream my implementation from scratch. I'm also much more likely to answer technical questions on the subreddit than through Facebook or Twitter or YouTube comments, and there's a lot of friendly people to help out, so if there's anything confusing in this video, feel free to post on there, and I hope you all give the challenge a try, even if you just started programming, even if you've never done programming, but as always, have a happy day wherever you are. I'll see you guys next time. Bye!